And you don't need me to do audio, right? The audio.
Yeah.
Thanks. Thank you for the introduction. Let's get started. So I have the same title as all of the other speakers today because that's the topic of the workshop. But I get to go first, so I guess my title is going to look original, and then everyone else will have a similar one. I think there's maybe like a little bit of philosophy behind that, which is this is actually the topic that's on a lot of people's minds these days in 2024. And I think that while the basic concept behind what a robotic foundation model represents, which is the possibility that we'll actually get robots, autonomous vehicles, all sorts of systems to actually behave intelligently in a broad range of situations, while that promise is extremely appealing to all of us, the practicalities of how we can bring that about raises a lot of question marks. So that's what I want to talk about a little bit today, how we can take steps towards real robotic foundation models that do for robotics what systems like GPT-4 and Gemini and so on did for NLP, and what are some steps we can take in that direction. But first, a little bit of motivation. The motivation maybe will not come at all as a surprise to any of you, but the way that AI systems used to work, the way that things here at CVPR worked maybe 5, 6 years ago is, well, whatever problem you might want to address, like let's say image segmentation or classification or anything else, you would collect a data set, typically you would label it, maybe you would put in a lot of work to get crowd labeling and things like that. And then you would train a large neural network model, and there would be different kinds of architectures for different applications, really good architecture for classification versus some fully convolutional thingy for segmentation, some kind of other thing for text summarization, and that would be your approach. And that was actually quite effective because if you get a large data set like that, you get really good results out of it. The problem is that it was very difficult to make these kinds of systems flexible. The system that was trained for classification was not really a great system for image segmentation. In fact, its performance on image segmentation was undefined because it simply could not be applied to it. And that meant that for every application, you would have to go through this whole process all over again. So, of course, the way that these things work now is we don't bother with any of that. We instead train extremely large models on basically everything we can get our hands on, which is these days mostly all of the internet. And then we call these things foundation models, and we find some way to adapt it to the task that we want to solve downstream. And we adapt it either with prompting or with fine-tuning, or sometimes a combination of both of these things. So that works really, really well. Why? Well, because if you have an application for which you don't already have the luxury of a gigantic labeled data set, you can simply load up one of these large pre-trained models that is trained on all of the internet to do all sorts of things and then adapt it to your task. And that works really, really well. It's a very flexible kind of general reasoning inference engine. So what about robotics? Well, how robotics works now is that if you want robots to do something, whether it's navigation, manipulation, or anything in between, you take your task, you set it up, you do a bunch of engineering. If you want to do robotic learning, you generate lots of data, and then you have a policy that hopefully does your task in a particular environment with a particular robot. And each time something changes, then you go through this whole process all over again, whatever weird task you want to do. And the more esoteric your task is, the less likely you are to be able to get that large data set because you have to do everything yourself. And this is probably one of the biggest barriers to the use of machine learning in robotics, that each domain actually requires a lot of bespoke effort to be put into it. So, of course, the natural inference from this is, well, can we somehow do the same thing that language models and so on did for other areas of machine learning, but for robotics? And we get this kind of internet of robotic data and somehow train something on it with a scalable, self-supervised objective, so that if you have a new robotic task, like, I don't know, sorting recyclables, you can just load up your robotic foundation model, get a few hundred trials, fine-tune it, or you can just prompt it in zero shot and get the policy that controls your robot to solve your task. Very appealing vision, but what are some of the questions that start to arise when we want to put this into practice? Well, there's a whole lot of questions, far more questions than I can possibly get through in this talk, but I do hope to get at least at some of these. For example, one question is, what kind of model should we use? And there are a few very interesting possibilities and some very strong arguments to be made for a number of different designs. What kind of algorithm or objective? The success of foundation models in NLP and vision very strongly relies on being able to use all available sources of data. And using all available sources of data means using very general objectives, which are typically self-supervised. Most data on the internet is not labeled with ground truth labels, so we use things like next token prediction, contrastive learning, and so on to provide scalable self-supervised objectives. What would be the equivalent of that for the robotic foundation model? Very big question. What type of representations do we hope to get? What is it that we're actually going to pull out of robotic foundation models? And there are very strong arguments to be made for different perspectives, including maybe they're about predicting video or simulation or modeling, or maybe they're just about straight up controlling the robot. Lots of important questions. What kind of data do we use? That's perhaps one of the biggest questions, and I'll have a few things to say about that today. But even downstream, once you get one of these things, how do you actually adapt it to your task? And what kinds of tasks can you adapt it to? What kind of things could it be suitable for? What kind of fine-tuning modalities? What kind of prompting strategies? What kind of downstream algorithms can it be compatible with? So these are all big questions, and I'm not going to answer all of them, but I will try to touch on at least a few of these today, the ones that I consider to be perhaps the biggest bottlenecks. And then for the rest, well, I'll leave that as an exercise for everyone else. So how do we build robotic foundation models? I'm going to cover this from three perspectives that are very complementary. I'll talk about some of our recent work on robotic foundation models for navigation and how we got from basic models that can control a variety of different navigation platforms to systems that can be fine-tuned flexibly for a variety of tasks. I'll talk about how we can take these ideas into the world of robotic manipulation and incorporate vision language models into the process and what that gets us. And then I'll talk about how we can combine data from very different heterogeneous robotic platforms and why we might expect that to actually be a really good idea to address that big data challenge. But let's start with navigation, and I kind of want to more or less go in chronological order because for the students in my group, this was actually one of the first topics we studied when we had started working on robotic foundation models a few years ago. We had this idea that, well, there's a lot of data of various ground robots on the internet that different research labs have put together. So we can actually put together a fairly significant and very heterogeneous data set of robotic navigation data, and we can actually start experimenting with robotic foundation models in that setting. This is work that we started doing actually at this point almost 3 years ago, so it was first published in 2022, 2 years ago. What we did is we had our own data sets that we collected for robotic navigation, and we also borrowed some data sets from other research labs for a variety of different robotic platforms. So my student, Luke Shaw, he assembled this data set that contained things from small-scale RC cars to full-scale ATVs. And then he tried to train very simple, flexible models on this. And remember, the key to make this pretty scalable is to use things that are as self-supervised as possible. So the particular training scheme that he chose to use is goal condition policies. Goal condition policies are very simple and appealing because you don't need to actually know anything about what task is being performed in the data. The outcome, some amount of time to the future, is considered to be the goal, and then you simply predict the action, and in this case, also the temporal distance between the current observation and the goal. The model that he trained takes in current observation and goal observation. Now it's trained on multiple different robotic platforms, so one would think that it also needs to know something about what kind of robot it's controlling. We experimented with a few ways of dealing with this. It turns out that actually you could do something very simple. You could give it a little context in the same way that a language model gets context. The context just consists of a history of observations from the last couple of seconds. One might not think a priori that this is actually enough to do the job, but it turned out to actually do the job really well. Kind of makes sense that if you see roughly how the robot is moving from its recent history, you can infer roughly what type of robot it is and what are its physical properties. Probably not the solution that would solve this in every general case for every possible robot, but for this particular data set, it turned out to be quite adequate. The goal condition policies combined with a topological graph for doing long horizon navigation, which is a fairly standard strategy for learning-based control in navigation. And that's basically the approach. Now, it's trained on 6 different types of robots, 8 different data sets. And one of the things we were very interested in is whether we could take these general navigation models, as we call them, and apply them to other types of robotic systems. And we actually got pretty surprising degrees of generalization, which kind of makes sense in retrospect, because for navigation, a lot of basic principles are conserved. But one of the things you can see here in the top left, this is a drone. Now, the drone is being controlled by the same exact model that is trained on these 6 data sets. There's no training data of drones whatsoever in the data set. There is a little catch. The drone is pretending to be a car by flying at a fixed altitude, so the altitude is not being controlled. But the steering and velocity are controlled by the model, and it basically works in zero shot. It can fly around hallways without collision. The camera view from the drone is very different from the vehicles, but because all the vehicles have different cameras, it basically generalizes. So this is in some ways actually very unsurprising, but it is kind of nice that it wants to work in some sense. Now we can go further. This is a collage of all the different evaluations, so you can see different kinds of robots, outdoors, indoors, navigating around furniture, navigating around hallways, navigating around trees, a lot of variability. But of course, sometime around 2023, the thing that you were supposed to do is take these things and put them together with a large transformer, which is what we did. And the next iteration of the system, which we call the visual navigation transformer, was quite a bit more general. Now, this model is still very small by language model standards, so it's about 150 million parameters, about, let's say, 2 orders of magnitude smaller than even the open source language models, but it does the job because the data set is also a bit smaller. And now it can generalize to other systems. For example, it can control a quadruped. It's not moving the legs here, it's just selecting the direction. So just like the drone, the quadruped is pretending to be a car, but nonetheless, different dynamics, different turning radius and so on, it basically does the job. We can also adapt it in interesting ways that sort of resemble prompt tuning. So we could take that goal encoder. So there's the goal image goes through an encoder. We can cut off this thing and train a different encoder that encoded the same tokens that we're using to represent the goal during pre-training. And instead of encoding a goal image, we can encode some other task modality, like, for example, turn-by-turn instructions, like the kind that you might get from Google Maps. Basically embed them into the same goal space, very much like how somebody might train a multimodal language model where they embed images into the token space, token embedding space. Here we embed other task modalities into the embedding for what would otherwise be a goal token. And then we can get this thing to do fun things like drive vehicles in Carla using a few hundred fine-tuning examples. So what is being fine-tuned is actually not the entire model, it's just this goal encoder to basically take turn-by-turn instructions, put them to the same transformer that's pre-trained on all that real-world robotic data. We can do some fairly rudimentary driving in Carla. This model is actually publicly available and people have actually used it. People have used it from all over the world from, let me try to remember what these are. So people send us something every month about what they do. This video here, this is from a university in Estonia that used this for orienteering. So they put this on their robot and it drives around the Estonian countryside and locates landmarks, which is pretty cool. This is from Finland, I believe, and this was a project on semantic navigation where these folks, they had their own system for the semantics part, and then they just used Vint for the actual navigation layer. And this is a drone project from, I believe, from Princeton that also used Vint as, in this case, a baseline. So these are kind of small things, but I think what's interesting here, and for those of you that work on robotics will probably recognize this is pretty unusual, is that we actually have a model where we just put the weights on our website and people can download the weights and they can run it on their robot. And that's very rare in robotics. Like usually some people can take your idea and implement it. Sometimes they can take your algorithm and run on their own data, but it's pretty unprecedented for someone to be able to literally take your model and run it on their own robot driving through the Estonian countryside. So that was pretty rewarding for us. And of course, we can do fun things like take it to a conference and run a demo. This is at, I believe, the BARS conference in the Bay Area. Interestingly, we never trained the robot on data around humans. We did have a lot of data in forests. So I have this hypothesis that the way it navigates around humans thinks that these are all trees, but it does pretty well here. Now, a lot of the really fun things we can do with foundation models have to do with fine-tuning. So one of the things we wanted to see is, can we fine-tune with RL? Can we fine-tune autonomously? So we took this multi-robot data set. We actually modified pre-trained to use offline RL rather than supervised learning. And then we tried to see if we could fine-tune it to a little RC car to learn to race in indoor and outdoor areas. So we run an online algorithm, and what you saw there in that clumsy video was the beginning of training. So it's initialized from other robots. The active space is actually different. Instead of waypoints, it's controlling directly steering and gas, but that's just a different head on top of the same backbone. And then after a bit of training, after about 15 minutes, fine-tuning, I should say, with online RL, this is kind of what we get. So not perfect yet, but it kind of has the idea. It's going around the hallway. Sometimes it gets a little stuck on the walls. And then 25 minutes in, it actually does pretty well. Now, in the third-person video, it kind of doesn't look like it, but this RC car is actually driving around this hallway at pretty much the same speed that Kyle, the lead author on this project, would do from the same first-person camera. And I will say it actually looks a little faster from the first-person view. Turns out that if Kyle uses his own eyes, he can go even faster. So human eyes beat robot eyes, but from the first-person view, it's about the same. Now, this is pretty cool because those of you that are familiar with DeepRL will recognize that training from pixels in 25 minutes is kind of surprising. So that pre-trained initialization from all those other robots is actually buying us a lot in terms of efficiency. Same exact thing works outdoors, so this is fine-tuned to drive on grass. It figures out cool strategies like going on a little concrete walkway in between the checkpoints. So the checkpoint's on the lawn, but then in between the checkpoints, it goes on the concrete path because, well, you can go faster on the path. Here's a first-person view. Pretty tough task. There's a lot of camera shaking. All the grass gets in the way. And this is also fine-tuned with online RL in about 30 minutes. So that's cool. We're getting a lot of cross-robot capability, generalization, and the ability to fine-tune to different situations in different ways using different algorithms. All right, so that's navigation. Now let's take this a little bit further. Let's go into an area where there's a lot more semantics, and that's robotic manipulation. So in studying cross-embodiment robotic manipulation, of course, one of the first things we had to do, just like in navigation, is assemble a data set. And this was a fairly complex effort because there is not as much robotic manipulation data lying around, so we had to go to many more places. So this was work that was led by Juan Bong from Google and my postdoc Carl Perch, and a large number of other folks contributed, so this is a pretty big effort. What Juan and Carl did is they put together a kind of a coalition of about 34 different research labs, I guess 32 if you don't count their own labs, Berkeley and Google. And basically they called everybody up and they were like, hey, if you've got robotic manipulation data, donate it to science and we will give you a checkpoint in exchange. Most people didn't really know what the value of a checkpoint was, but it was fun, so they sent over the data. And then Juan and Carl spent a few months just converting everything to the same format. We ended up with 311 scenes from 21 different institutions, a total of about 1 million episodes, 22 different kinds of robots, 527 different skills, depending on how you count, and it was kind of a giant mess. So there's lots of histograms, lots of pie charts and so on, but I think that in a talk like this, it's probably easiest if I just show it. Apologies, let me restart this so that the videos will play properly. Sometimes PowerPoint gets a little bit with this. Okay. All right, so there's our videos, and you can see that there's a lot of heterogeneity in there. So all of the trials that were used in the actual experiments consisted of single robotic arms with parallel jaw grippers. We did have other types of robots in the data set, but we didn't use them in our final experiment. So these are just single arm parallel jaw gripper. But even there, you can see there's a huge amount of variability. A lot of variety of viewpoints, a lot of variety of robot types. They're doing all sorts of weird stuff. Some of them are making coffee. Some of them are loading dishwashers. Some of them are doing whatever this is. So there's a lot of stuff going on. It's very heterogeneous. And compared to the kind of data sets we use for robotic learning, it's basically the Wild West. So what did we do? We took all this data. We trained a language condition model on it. We actually trained two types of language condition models, but I'll tell you about the simpler one first. So the simpler one was structurally very similar to Vint. It was the model is RT1, which is actually which came before Vint, but same design. It's a transformer that takes in the current observation, some kind of task definition, which is in this case language, and then predicts actions. And then we took this model and we sent it to 7 of the labs that donated data. Here you can see videos from 4 of these. And we asked them to basically take this model and compare it. Compare it to what? Well, this was basically the first real cross-embodiment manipulation model. So we asked them to compare it to whatever their best model was for their data set, because they made the data set, so presumably they knew what to do with it. So what you can see here is the gray bar. This is just a baseline where we asked them to train the RT1 model, the same model in just their data set. The rainbow colored bar, this is the cross-embodiment model. And whatever bar is here on the left, this colored one, this is their best method. And on average, this is the average score, the cross-embodiment model was about 50% better in terms of success rate than whatever the best model that each lab had. And this is actually like, to me, this is actually even more remarkable once we kind of pause and think about what this means, because whenever you do research, especially in robotics, I think roboticists are even more guilty of this than most others, you kind of favor your method a little bit. Like you set up your task and then you have your method and then you kind of change your task and then you change your method and then eventually your method is really good for your task. Here we just sent a model to a bunch of people. Admittedly, these were very capable researchers, but they weren't like incentivized to make this model look good. They were just incentivized to drop it in there and run it compared to their method, which they've been tuning on their task, and just see what it does. And it does 50% better. So I think it's actually pretty interesting. I think this actually suggests that there's this benefit of generality, where the general purpose model is actually doing better on the specialized tasks than the specialists that were designed for that task. It's just kind of old news in the world of NLP and computer vision, but it's not something that roboticists are really used to seeing. Now, I mentioned there were 2 kinds of models. There is a second, more sophisticated model that we experimented with. And to tell you about that one, I need to provide a little bit more backstory. So one of the things we had been doing separately from this, but in parallel, is investigating other kinds of model architectures that could be suitable for robotic foundation models. And one of the things we were really interested in is whether large language models could be fine-tuned to control robots directly. So we had done some work on large language models doing higher level control with things like SACAN and PaulMe, but we wanted to see if we can actually have the robot policy itself be a language model. So this was work that was done in mid-2023, and what we tried to do here, this is a project called RT2, is we took a vision language model. This was what later became known as PolyX. At the time, it had a more secret code name. And PolyX is basically a classic multimodal large language model. So it's a language model backbone that is fine-tuned with an EIT encoder and encodes images into the same token embedding as the language model. Very classic recipe. And then we took this thing and we then fine-tuned it to output actions. Now, how do you get a language model to output actions? Well, there's some really clever ways you could do it, but one thing you could do is you could literally get it to print numbers, like, literally just like the ASCII characters, and that actually works. There's probably much better ways to do it, but we didn't have time to figure out better ways, so we just had to print numbers. And then you could do stuff like you could give it commands like put the strawberry into the correct bowl, and it will basically speak robot actions and move the arm and do that task. Now, this might seem like a little bit of a funny exercise because you're kind of taking this model that's designed for things like visual question answering and then torturing it to output numerical action values. So why might you want to do that? Well, it turns out that if you do this right, you actually inherit a lot of those rich semantics, a lot of that semantic knowledge that's contained in the vision language model. So you can do fun things like specify tasks for which the robot data can't possibly be adequate to get the robot to do it. Like you could say, move the Coke can to Taylor Swift. I promise you we did not have any robotic demonstrations that have pictures of Taylor Swift, but the robot definitely knows who Taylor Swift is, and if Taylor Swift needs a can of Coke, it'll gladly give her the can of Coke. You can also do fun things like give more nuanced instructions and actually use the semantic reasoning capabilities in language models to essentially do chain of thought where the end result is an action. You could say things like, bring me a drink, and it will figure out that to bring a drink, it should pick up the 7-Up can because the 7-Up can is a drink. So if you just told a regular non-BLM policy, bring me a drink, it would understand that just because of the nature of the labels in the data. You can figure out, well, 7-Up can is a drink, there's a 7-Up can, so let's output the actions to do that. You can even do more complex things, like you could say, here's a picture of here's what the robot is seeing, there's a table with some rock and a sticky note and so on, and it says, I need to hammer in a nail. What object from the scene might be useful? It figures out that it's a rock, and then outputs the actions to go and pick up the rock. So these are fairly rudimentary examples, like, giving the Coke can to Taylor Swift is probably not the be-all, end-all application of robotics, but it does give us that little sense of how the deep semantic knowledge and reasoning capabilities in vision language models could actually be integrated into robotic control in an end-to-end way. So, of course, what we want to do with our large cross-embodiment data set is see if this kind of vision language model could also improve from integrating data from many different robotic systems. This is not at all an obvious hypothesis because, of course, the vision language model already makes this policy very, very powerful. So one might suppose that the null hypothesis, that basically the VLM already gives it so much generalization power that all those little robotic data sets wouldn't really help, that null hypothesis is quite probable. So we wanted to test this out, and we created RT2X, RT2 train on cross-embodiment data. And we stress tested it on a variety of tasks that they're almost like designed like a robot intelligence test. So we gave the robot a variety of semantically fairly challenging tasks that involved relationships between objects, like move the apple between the can and the orange, those kinds of things. These were basically designed to be things that were pretty difficult even for the original RT2 model to handle. And this is what we saw. So we saw that just by changing the data set, including that cross-embodiment data for many robots, performance on this suite of fairly difficult semantic tasks jumped by about 3x. And that's a very big improvement. Here are some more examples of what these tasks look like. A lot of them have to do with these semantic relationships. Put the orange into the pot, move the orange near the pot, object relative motion, move the apple between the Coke can and the cup. And it turned out to be a lot better. So you get a lot of benefit out of having the rich semantics and vision language models. We also get a lot of benefit from including all the robotic data you can get your hands on, even if it comes from other robots. And I'll also mention the robot we tested this on. This is the Everyday Robots robot. It was the robot that was the most overrepresented in the data set. So this was the robot for which there is the most data. And even the majority robot actually benefits significantly from all those other data sources. Okay, other things that are maybe more interesting to this audience in this area, if you want to get into this cross-embodiment robotic foundation models research yourself, we released a model called Octo, which is a open source model designed for cross-embodiment research. It's a very flexible model that can take in different types of task specifications, language, and goals, and can be readily fine-tuned to different output modalities. So Octo is basically, you can think of it as like a really big version of Vint with a variety of different input modalities. Octo does pretty well in zero-shot evaluation, so we compared it to RT1X and RT2X. These are what we refer to as in-distribution tasks. So these are not tasks that are meant to stress test generalization. They're meant to test basically your ability to put the data. It does pretty well in those things. So these are 3 different robots that were visible in the pre-training data set, and it does significantly better than RT1X, and actually often matches the much larger RT2X model. The RT2X model is still better when it comes to difficult generalization problems, but for the in-distribution tasks, it's very similar. We can also take the Octo model and we can fine-tune it with a small number of trials, something on the order of hundreds of trials, to a wide variety of different tasks, and it's really designed to be fine-tunable. It can be fine-tuned even to other action spaces like the bimanual system, this is the Aloha system. So these are a few videos of the kinds of tasks that Octo can be fine-tuned to. And that's really important because, of course, if you want to grab this model and use it yourself, chances are you're going to be fine-tuning it to your own data. Now, of course, if you want the VLM component, very recently there was a project, a collaboration between Stanford, Berkeley, and a few other labs called OpenVLA, which aims to provide an open source vision language model fine-tuned for robotic control. OpenVLA is exactly what it sounds like. The core VLM that it's based on is prismatic VLM, and it's fine-tuned to output robotic actions with the same RTX dataset. OpenVLA generalizes really well, so this is another one of those hard generalization evaluations. It's actually a different one than the one that was used in RT2X, just because this was done at a university with a different set of tasks. But performance is pretty good. We were able to get a comparison to RT2X using the API version, and yeah, it's pretty good. On in-distribution tasks, it kind of is similar to RT1X and Octo, but on other distribution tasks, it's quite a bit better. All right. Now, in the last portion of today's talk, I'm going to talk about how we can push this cross-embodiment idea even further. So far, we had a little bit of a trick. All those navigation experiments all were first-person navigation on a 2D plane. Even the drone was pretending to be a car. It basically goes to 2D checkpoints, PD control to a 2D location in front of it. The arms were all single arms with parallel draw grippers. So that's pretty convenient because you can use forward kinematics, same action space, etc. But what if you want to use all the embodied data you have from whatever kinds of robots you might get? Can we push this even further? Can we, for example, take our data with robotic arms, incorporate data from cars, incorporate data from legged robots, arms, vehicles, everything we get our hands on? And why might we expect that to be a good idea? So there were a couple of papers that we released recently that studied this. The first one by Jonathan Yang, called Extreme Cross-Embodiment, aims to narrow in on a very particular aspect of this problem. Can navigation and manipulation data be combined to lead to better generalization? So what we did in this work is we took data from robotic manipulators as well as mobile robots, legged robots, again, legged robots just controlled in terms of waypoints, autonomous driving data, and ground robots, and tried to see if we can combine it all into one. 1 second, let me start this. Just keep breaking. Yep. Okay, so here are just some animations of the kinds of episodes that are in the training set. You can see that there's some manipulation with wrist-mounted cameras and navigation on the different kinds of platforms. And the reason that this might help is that at some level, the physics and geometry of the world is the same, whether you're controlling a robotic arm or a ground robot. So this is Jonathan and Catherine prepare these little videos to kind of illustrate that point. That you can see that if you're trying to approach the apple on the table, or you're trying to pick up a strawberry, you have a wrist-mounted camera versus first-person camera on the ground robot. The relationship between your actions and the change in the viewpoint is basically the same. So there's the same kind of visual servoing primitive, the same kind of geometry, the same kind of physics. So insofar as you can get at those underlying concepts, you'd expect them to be conserved, and therefore you'd expect to see forward transfer. You'd expect to see positive transfer across these embodiments. So does that happen? If we train one model across all of this, well, first, does navigation help with manipulation? So if we want to solve manipulation problems, we include navigation data, does it make it better? Of course, Probably want to know, does it make what better? So these are just some videos of those manipulation tasks, just to remind you. And these, the different groups here are different tasks. The different bars are different models. The solid green bar is trained on only manipulation data. The striped green and blue bar is trained on manipulation and the GNM data set. The GNM data set is the one that we used way back at the beginning of the talk for those cross-embodiment navigation policies. And the green, blue, and yellow striped bar also includes BDD100K, which is an autonomous driving data set. And you would think that autonomous driving has very little to do with grasping strawberries, but it turns out that even that helps. So the average you can see here, about 20 points of improvement from only manipulation to including all of the navigation data. So knowing how to drive really helps you pick up those strawberries, and now it's a proven fact. Does manipulation help navigation? There actually, the evidence is more mixed. We're not sure why. Maybe it's because navigation data is so much more diverse. So it does help a bit, but definitely not as clear cut. So this is a more complex experiment. These are the videos. The blue bar is only the GNM data. So this is the data from those 6 different robots driving around. The yellow stripes include driving data. We're probably underfitting. We need bigger models and more GPUs. When you add in the green stripes, that's the manipulation. And then green, blue, and yellow is all of the above. So pattern here, well, probably the real pattern is that driving data is making us underfit, and we need a bigger model and a bigger GPU. But if you disregard that, it does actually seem like it. So definitely more mixed, definitely more research needed, but it seems like something good is going on. All right. Now, there is a little trick that I wanted to tell you about that we used here. The trick is that in all of these cases, we were using egocentric cameras, so wrist-mounted cameras on the arms and first-person cameras on driving robots, and actions that are in the coordinate frame of the camera. So the action space is actually the same for all of these systems. So it kind of makes sense that, yeah, like you kind of make it into a visual sobering problem and you benefit from visual sobering. So can we lift that assumption? Because aligning all those action spaces is kind of a pain and it might not even be possible in the general case. So can we make it even more extreme and literally just dump a bunch of different robot embodiments into a model and train one big model to control all of them? And it turns out that we can. So here's the design. This is a model that we call Crossformer. It's a model that has basically different action heads for different action spaces, but otherwise shares most of its parameters across different robotic configurations. And finally, for these legged robots, we're actually going to control the legs. So here, every robot is controlled in its native action space, controlling the legs for a legged robot. Single arms are controlled in end effector space. Bimanual systems here are controlled in joint angle space because that's what prior work did, so different action space. And then the ground robots are controlled in terms of waypoints that are about a meter in front of the robot, so basically 2D locations on the ground. So it's one big model treatment, all of this, and it does pretty well. Here, this is kind of one of the most surreal comparisons I've seen in a robotics paper. All these different groups of bar plots are different types of robots, ranging from single arms to Aloha, which is dual arm, Locobot, which is the ground robot, and Go1 is a legged robot where you're controlling the legs. Yes, this thing actually helps. It does better than single robot policies, and it does better than whatever is the best environmental model that can ingest all the data. It also does significantly better than the previous method I discussed, which is not all that surprising because this model is really designed to deal with variable action spaces. But it's maybe a little bit more compelling if I actually show in detail what each of these embodiments looks like. So this is just a sampling of the kinds of things that we tested. These are the single arms, so these are basically language conditioned or role conditioned manipulation tasks. This is the bimanual system, it's the Aloha system. It doesn't look all that different because it's just 2 arms, but it's controlled in a very different way. It's controlled at 50 hertz with large action chunks and joint space, whereas these are controlled at much lower frequency in end effector space. So they're much more distinct actually than they even look. These are the navigation experiments. For the navigation experiments, these models are also combined with topological graphs to do long horizon navigation. So this is embedded in a pretty different kind of overall robotic system. The legged stuff, still running this in the real world. So this is a simulated experiment, but yes, it is actually moving the individual legs. So the action space here is 12-dimensional control of set points for the leg joint angles. Okay, so to summarize, I think from these discussions, perhaps there's an image forming of what my opinion might be about how we build a robotic foundation model. That opinion might be actually fairly straightforward. Take all the data you can get from all the robots you can get your hands, all of them. And then take a model that is already very, very good, like a vision language model, turn it into a vision language action model, fine-tune it on the robot data, And then you have your robotic foundation model and then use it in as many possible ways as you can. Use it in zero shot, fine-tune it with some prompt tuning to do some driving, fine-tune it with RL to do fast racing, utilize it for downstream instruction following, go wild, use it for whatever you want. And as long as you use a really nice, big visual language model, and as long as you use a really nice, big, diverse data set of all sorts of different robots, maybe you'll get some approximation of the kind of capabilities we want out of robotic foundation. That's it for my talk. We recently started a company called Physical Intelligence to basically see if we can instead these things for real. This is very much a work in progress. I'd love to talk to you more if you're interested. But I want to conclude. I want to thank my students and all of my colleagues who carried out this research. And I'd like to thank you for listening.
Any questions from the forum? Yes. Do we have a mic?
Yeah.
And is quiet.
Can you share some learnings about what's important when you file all the data together? You know, maybe from the critical analysis different sources.
Yeah, so the question was, what did we learn and about what's important when we file all this data, data together from all the different modalities? There are a lot of things that are important. Unfortunately, these are things that are hard to put into concrete rules. One thing that's really important, and this is very annoying, is balancing the data. It is extremely important to balance the data properly, and we have no idea how to do it. And if you do it wrong, then the thing doesn't work. If I had to guess as to a principle, the principle is you want to weight your data in proportion to the amount of useful information contained inside of it. Unfortunately, I don't know how to determine the amount of useful information contained in the data set. But this really matters. And it's not as simple as just upweighting the robot you're testing on. It's not as simple as upweighting like the coolest robot or the most interesting robot. And it really, really matters. And this is very important. For what it's worth, the folks that are working on language models and vision language models have to deal with the same thing. So the choice of your trading mixture is important. So maybe it's kind of comforting, but it's also important for robotics. Other stuff. We do have to still take some care in regard to action spaces. I think we're getting a lot better at handling heterogeneous action spaces, but it's very easy to go horribly wrong with like, like I have velocity control, but my velocity is represented in like degrees per second instead of radians per second, and it's not normalized correctly. So all those little details kind of matter. But I think that's the thing that's actually getting easiest and easiest over the last year. So maybe a year from now, this won't be as tricky again. There's probably a half dozen other things. Unfortunately, they all fall into that category of things that are where I don't have like really good answers about what to do, just things that are difficult.
Yeah, so thanks for the great talk. I'm Rensheng from Remote Research. So for the last section, you showed that using the travel data can help picking up the strawberry. Do you have any guides why can that happen? And also, if we do in the reverse way, picking up the strawberry, will that help the dragon?
Yeah, that's a really good question. So I think there's a lot of speculation. One thing I will tell you, which we did actually examine to the best of our ability in the paper, and I would encourage you to check out the paper for that, is the degree to which what's actually being transferred is essentially like a visual servoing skill, and that does appear to be happening. So we have a few experiments that provide circumstantial evidence for that, and that kind of makes sense because basically, if you're doing navigation, you learn some very basic geometric things. Like if an object is small and far away, and you move towards it, it gets bigger, right? And that's true for whether you're reaching for a strawberry or driving a car. I think that it remains to be seen further on from that, the kinds of concepts that can be effectively inherited. And this is a very difficult thing to study because the ability for a model like that to distill out the fundamental concepts instead of pick up on surface level patterns requires enough data that the true underlying concepts are actually apparent. So it may be that the much more sophisticated kind of transfer will be hard to understand until data sets are at the right scale, until you get that kind of emergence effect that we've seen in large language models. So the short answer, geometry, visual servoing, the basics of how 3D worlds work. The longer answer is we won't know for sure until we scale it up enough.
Yeah, all right.
I have a short question. So there's a clear trend that usually people are adopting the billion-scale large language models as the backbone for robotic tasks. But the thing is, the robotic instructions are usually not as complex as writing fictions, answering a variety of questions. So is there really a need to adopt such large capable model as the backbone for the robotic tasks, as robotic tasks are usually requires the efficiency?
Yeah, that's a really good question. I'm glad you asked that. I would like to give my robots more complex instructions. I would like to tell my robot, you are a robot bartender. Be a good bartender. Now, any language model worth its salt can figure out what that means. If you ask GPT-4, what do you do to be a good bartender? It'll probably tell you a lot of things, probably more things than you even want to know. So the knowledge is in there, which means that we can essentially, in the future, treat these kinds of models almost as like robotic operating systems, where you write your robotic application in English. Like you take literally the manual for the job that you want the robot to do, give it the manual, and it does the job. And I think that'll be a very complex problem. We're nowhere near that. Like right now, we're picking up pictures of Taylor Swift, but I think we'll get there someday. And I think that large multimodal language models will help us get there. Yeah, very good question. I unfortunately don't have a car that I can use for autonomous driving experiments. I do think that'll be really fascinating. Now, I think there will be additional challenges that come up, but I think that one of the really interesting things about autonomous driving is that in contrast to like driving one of those robots through a hallway, autonomous driving is very semantically rich. And sometimes, you know, a lot of what we do when we actually build practical autonomous driving systems, we bake that semantic richness into a bunch of rules and we work really hard to encode them. But there are semantic rules. Like you could, in the same way as the robotic bartender, you could literally give like, you know, the state of Washington driving exam to the VLM and see if it'll figure out how to drive the car with some rough approximation to the rules of the road. I think that'll be really interesting to study. I haven't gotten to that, and I don't have an autonomous car, but if anybody's interested in it, OpenVLA is out there, and you can grab it and you can fine-tune it for driving. You can give it lots of complex prompts and see if it'll yield to pedestrians and do all the other things that maybe drivers in Washington State aren't as keen to do. Yeah, any other questions?
Yeah, wanted to get your opinions on, are you familiar with the VJEP architecture from the where do you see incorporating that into your future?
Yeah, this is a really good question. And I think that maybe something that is underlying your question is the role of models and prediction as compared to policies. The question was, well, how does this compare to the VJEP architecture, the one that Jan McLean was famously advocating? So I think the bigger thing underlying this question is the role of models and prediction in this context. Everything that I presented is very unashamedly about policy learning. And policy learning makes a lot of sense if you want to kind of get the ball rolling on these things because, well, policy learning, like if you get a policy, you control the robot and you're kind of done. At the same time, there's a very good argument to be made that prediction is a really good objective to use in this context because you can learn to predict from lots of data that is difficult to use for policies. And it makes sense to incorporate prediction to things like this. In fact, we already did that to some degree, to a very limited degree in the VINT model, because the VINT model was actually predicting reachability. Now, reachability is not the same as predicting future states, but it gives you a little bit of a proxy of that. It's kind of value function. My own, this is maybe getting too much into the weeds, but my own opinion on this is that actually there is not a dichotomy between prediction and policies. There's actually kind of a smooth gradation where you can predict progressively higher and higher level concepts. So things like reachability, value functions, they're also predictions. They're a little bit model free in nature, but they're a little bit model based, all the way to full on prediction of states. And I would argue that the JEPA type design is kind of also in that middle ground where it's, well, it's not predicting raw states, but it's predicting embedded representation. So I think there's a big spectrum there between fully model free prediction and fully model-based prediction. I think exploring that spectrum is a really fruitful thing to do, particularly in regard to getting better self-supervised learning objectives from large amounts of sequentially structured data.
Yeah, we might have the last question.
And I wonder if those kind of perception from robots and offline, like,
yeah, that's it's an interesting question. I think there's actually a lot wrapped up in that. So there has been a fair bit of work on incorporating vision language models into systems that involve an ensemble of different models. And the way this pertains to your question is that one design that folks have explored to a considerable degree is something where there are separate perception systems that are queried as tools by a language model or vision language model. And that's actually kind of a pretty neat design because you can imagine that, like that chain of thought example I showed with the rock, you can imagine a much more advanced version of that says like, hey, I need to find this type of object. Let's call an object detector, figure out where it is. Let's paste in the output from that object detector into my prompt and use that and then call some other model and so on. So you can kind of stitch together a system out of these different models. In the olden days, we would do this in robotics using ROS and using lots of subscribers and publishers. But now that it's 2024, maybe we do this by using a language model to actually make those queries to those tools. And you could imagine it almost like as an embodied chain of thought process. There's quite a bit of research on this, including from my colleagues, including from many other labs. I think it's a pretty exciting area, and we'll see